Hello, everyone. My name is Karol Latecki, and I am an infrastructure and DevOps engineer working at SPDK project. In this presentation, I would like to talk about and show you how in SPDK we do performance benchmark tests. Quick stop at obligatory notices and disclaimers slide. And let's start with the agenda. We'll start by discussing what's measured as part of SPDK performance tests. Then we'll talk about our per release performance reports. And after that, we'll go into a bit more detail describing what are the specific test cases which contribute to those performance report documents. Finally, we'll take a look at some optimization settings used in testing to improve the overall performance. So first, let's talk what do we at SPDK mean when we are talking about measuring I/O performance. The first metric is IOPS per core. SPDK pulls hardware from user space, and with this metric, we can measure how efficient is SPDK in doing that, in processing I/O when using a single thread to do the job. The second metric that we mention is the I/O core scalability. Here we measure how the results change as we use more CPU cores to perform the I/Os. And the third very important metric that we measure is the latency. Both average and tail latencies up to 4 nines. SPDK, which is working in polling mode, is expected to have an effect of reducing latency and its variability. Once the performance tests are complete and the results are collected, they are then put into a report document, which is published on our website, SPDK.io, in the performance report section. You can find all of our reports for almost every SPDK release from the past few years there on this website. These documents contain detailed description of test setups and results breakdown, and the upcoming slides in this presentation are basically an overview of what's included in those documents. Now, as mentioned the previous slide, we do performance benchmarks every release, but why? It is a time and resource consuming process, so there's a question, do we really need to do benchmark tests on every release? And the answer is pretty obvious in case any hardware changes were done to the test systems that are used for the benchmarking process. We tried to update our hardware configuration so that it does not over time become a bottleneck for the software we're testing. So every time we change it, we need to rerun the tests. Per release benchmark tests also serve as a regression tests in a way. And in almost every release, our team either introduces completely new features, which sometimes should or should not have effect on the performance of existing code, or the team makes extensive software optimizations to already existing critical paths in the code. Thanks to our regular benchmark tests, we have an insight into SPDK's performance, whether it has changed, improved, degraded since last release. It also gives us an opportunity to highlight any benefits of any software optimizations or new software features that may have been added during the current release development cycle. And now talking about regression testing, long and extensive per release performance tests are great, but they do have a downside, as they don't allow for enough flexibility and quick reaction to any code changes that result in performance degradation. Because we want to quickly detect any performance regressions, we also run a quick version of those benchmarks as part of our continuous integration system. While the same set of automation script is used to generate the results, those continuous tests are not an equivalent of quarterly reports and serve us primarily as a tool to early detect and report any introduced regressions, just like in the screenshot on the right. You can find the live versions of those dashboards at performance.spdk.io. The link is on the top of the slide. And just one more slide to show how the performance dashboards look like. The trend is easily visible in the charts, and the tables provide information about row numbers along with commit hashes, so any faulty changes can be quickly identified, reported, and fixed. All right, let's go into a bit more detail and talk about the test cases, objectives, and methodologies in SPDK's performance benchmark process. For testing performance, 3 storage usage models are used, and these are local block storage, networking storage, virtualized block storage. And we use 2 block sizes in our tests. Typically, these are small workloads with 4 kilobytes block size with 3 workloads. These are 100% random read workload, 100% random write, and 70-30 mixed random read-write workload. Additionally, we use workloads with large block sizes with 128 kilobyte block size, and these are 100 sequential reads, 100 sequential writes, and a mix of 70-30 sequential read and writes. To run these workloads, we use various benchmarking tools. We're primarily using FIO, which is an industry standard tool. It is very flexible and has a ton of options and reports quite a lot of metrics. It's great to use in any case where we want to compare SPDK with kernel counterparts, because it can both work with kernel block devices as well as in user space with SPDK, thanks to the 2 plugins created by our team. One of those plugins is using the NVMe driver directly, and the other one works with the block device layer. We're also using our own SPDK performance tools. They are a bit less flexible than FIO, excuse me, and they don't offer as many features, but they are better optimized for the SPDK usage model of submitting and polling IOs. And because of the reduced feature set, they have less overhead. And similarly to FIO plugins, we have 2 tools, nvme-perf and bdevperf, that either use the NVMe driver directly or work with the block device layer. Some of the performance tests that we run as part of our benchmark routine use null block devices, and this is mainly for latency measurement tests. However, the bulk of testing is done by using NVMe SSDs as backend devices. And in order to provide consistent and repeatable results, physical NVMe drives need to be preconditioned before running the tests. SSDs can show different performance levels depending on the write history. Fresh SSD drives, ones straight from the factory, have all their pages free and will show much higher performance than what's described in their technical specification datasheet. This is because the drive's controller firmware does not have to look for free blocks or free pages to perform write operations, because all of them are free anyway, or immediately returns null when reading from an unallocated block. And for drives that have been already written to, there's SSD's controller garbage collection algorithms, which also play an important factor because of the optimizations which are done in the background for already allocated blocks. Because of that, it is important to reach the disk steady state before running benchmark tests and collecting performance data. Reaching a steady state means moving an SSD from a fresh state to a state where the drive's real performance is, so that the results are similar between each test run for a given workload. Now, how do we achieve that? First, we need to fill the SSD's capacity, including its per pages, to a maximum. And this is done by performing sequential writes to the drive at least twice. The next step is to precondition the SSD using maximum queue depth used in the test-specific workload until we reach steady state. So for example, we would use random writes if we were then testing random workloads performance later. We run this preconditioning step until reported SSD's performance stops fluctuating. And this step can take very long, depending on the SSD's capacity and and garbage collection algorithms run in the background. And after that, we're finally ready to run the test workload and collect the performance data. Now, it is important to transition seamlessly between all those three phases. Let's now take a look at SPDK's use cases and test scenarios in a bit more detail. And let's start with local block storage. For local block storage, we have 4 test cases, which are focused on measuring efficiency, scalability, and latency of SPDK NVMe block layer. We configure the benchmark tool to use SPDK NVMe block devices. And in the first test case, we run a small block workload with high queue depth and measure the maximum number of IOPS that we can get using a single CPU core. We also do the same tests with just using the NVMe driver so that we can show the overhead of using the block layer instead of using the NVMe driver directly. And for the second test case, we do a similar thing, but this time we increase the number of used CPU cores so that we can show and measure how the performance scales with the addition of those new cores. Now, for those 2 test cases, we are using our own testing tools, previously mentioned nvme-perf and bdef-perf in order to maximize the performance and reduce needed CPU resources to do so. And for the next two test cases, we switched to using FIO along with FIO plugins. So in the next third test case, we run the workloads with the QDepth set to 1 in order to measure the latency. And we are using SPDK's FIO plugins. Thanks to that, we are able to compare SPDK's block layer performance with kernel's block layer, which are utilizing FIO, IOUring, and libIO IO engines. And in the last fourth test case, still using FIO, we limit the number of IO cores used in the test, and we check the performance scalability, but this time we scale and increase the QDepth from 1 to 512 and compare the performance results for SPDK and kernel alike. Let's take out some example results from mentioned test cases. Those results come from a system with Ice Lake CPUs installed with 22 NVMe SSDs on board. If you're interested, you can find detailed descriptions and specifications of our test platforms either at the end of this presentation or in our performance report documents. The workload we're using here is 4K random read with QDepth 192. This is all running on just one CPU core, and as you can see, the performance scales linearly with addition of up to 5 NVMe SSDs, and then later peaks when using 6 SSDs with the result of about 6.7 million IOPS. SPDK NVMe block layer performance scales as we increase the number of IO cores used by the benchmark. And for the 4K random read workload, you can see that the IOPS scale linearly to almost 30 million with just 5 CPU cores, which saturates NVMe SSDs installed in this platform. We can also observe linear scaling for other workloads for random write and random read-write workloads, although the IOPS results, the IOPS values are not as high because of the limitations of used NVMe SSDs. And finally, in the fourth test case where we use FIO and FIO plugins to compare SPDK and kernel's performance, we can see similar high performance results. Here we limit the number of available cores when doing the IO to 12 and scale the workload QDepth to test both SPDK and kernel block layers. For all tested cases, either using SPDK or kernel, you can see that the performance was similar up to about QDepth 16. And beyond that number, we can see the polling implementation of SPDK showing benefits as the performance difference between SPDK and kernel becomes clearly visible. Let's now move to storage over network. The test objectives for networking storage are primarily measure the performance of SPDK NVMe over Fabric's target and initiator components. We also compare the performance of SPDK and kernel NVMe over Fabric components. And we conduct our tests using TCP and RDMA transport layers. The test cases for storage networking are pretty similar to what I've already talked about in the previous section for local storage. And the first test case is testing SPDK NVMe over Fabrics target IO core scalability. The main knob in this test is the number of the target CPU cores. The CPU cores on the initiator side are fixed and do not change during the test. We then run various read-write mode and QDEF combinations and aim to reach the highest possible IOPS result, preferably reaching either network link saturation or reaching NVMe SSDs on the target side saturation. Test case 2, it's pretty much identical to test case 1, but in turn, this time we're testing how the SPDK NVMe over Fabrics initiator scales with the addition of IO cores. So this time the target CPU cores are fixed and we scale the number of initiator cores. Next, test case 3 is about measuring latency for both SPDK and kernel nvme-of components. Here, like in the local storage, we use random type workloads with small block sizes, 4K, using QDEP1. And additionally, we check various combinations of target and initiator modes, mixing SPDK and kernel to see mixing SPDK and kernel on both sides of the connection to check their interoperability and to see what's the impact on latency performance. And finally, there's the fourth test case, which is checking the performance along with the increasing number of connections. So this time, instead of increasing the QDEP or increasing the number of cores, we scale the number of connections that are coming to nvme-of target subsystems. Our test setup consists of 3 server systems. The target system is the one with installed 14 NVMe drives, and the other 2 are initiators responsible for initiating the connections to the target system. All systems are equipped with high bandwidth network interfaces so that network link does not become a bottleneck for performance testing. And currently, in total, between target and initiator systems, we have 400 gigabit link available. Our tool of choice for benchmarking NVMe over Fabrics is FIO, because like I said before, with plugins, it can be used both for testing SPDK and kernel initiators, and that allows us for easy comparison between them. Okay, let's take a look at some example performance data for storage over Ethernet. For this presentation, we have picked TCP data, but if you're interested in RDMA, then please go check out our performance reports at SPDK website. Those are available there. And as you can see in the chart for 4K random read workloads, the IO performance of SPDK NVMe over Fabrics TCP target scales linearly up to 12 CPU cores, which allows it to process well over 200 gigabits of traffic. Now, further adding additional CPU cores results in less linear performance improvements, and the peak is reached when using 32 CPU cores, which allows to saturate 400 gigabits network link. Now, this chart shows, once again, performance scaling of SPDK nvme-of target, but this time the workload is sequential reads 128K block size. And as you can see, with just one CPU core, SPDK target is able to process 200 gigabits worth of IOs, and with 4 cores or less, up to about 400 gigabits per second. For Storage over Fabrics benchmark report, I would also like to highlight SPDK's feature, which allows to change its scheduler mode. By default, SPDK runs with static scheduler, which starts polling threads on all CPUs specified in the CPU mask. In case of less demanding workloads, this results in overutilization of the system's CPU resources, as most of the pollers don't do any real work. Switching SPDK's scheduler to dynamic mode allows to group idle polling threads on the same CPU core and reduce overall system CPU utilization, which in turn also results in smaller power consumption over time. All right, and finally, let's check third tested storage type, which this time is virtualized storage. In virtualized storage tests, we utilize SPDK vhost to provide local storage as a process to expose block devices to other processes, like, for example, virtual machines. The benchmarking process and the test cases here are, well, similar to what has been already told for previous section, local storage and storage over fabric sections. So let's go quickly through those cases. And for virtualized storage, the test cases focus on measuring the IO when using a single thread SPDK vhost target, testing vhost IO scalability with addition of CPU cores, checking SPDK vhost performance when serving IO for a large number of VMs, and finally, testing latency and the IOPS results with increasing queue depth. For virtualized storage tests, we primarily utilize SPDK and kernel vhost SCSI and vhost block stacks, but recently we're also adding VFIO transport into the mix. If you're interested in how VFIO compares to vhost, then you should check out our 2209 vhost performance reports, which will contain this comparison. All right, let's see some numbers now. Like said, when running core scaling tests for vhost, we check various vhost stack and block device combinations. And in this chart, we present scaling results for both SCSI and block stacks when using NVMe and logical volume block devices. The number of QEMU virtual machines attached to vhost controllers in this test goes up to 36. And with our current hardware setup, we were able to get a peak result of about 7 to 8 million IOPS, depending on the used vhost stack. And here we can see the results which show IOPS when SPDK vhost is constrained to use just 4 CPU cores. We have limited the maximum number of IOs for each virtual machine to 10K, and we are scaling the number of VMs connected to SPDK vhost controllers. As you can see, SPDK is able to process all of the IOs coming from up to 72 connected virtual machines. Now, for each of the tested storage types, we apply settings for optimal performance. Typically, for each tested storage, we apply a set of configurations and best practices to improve the overall performance a bit more. Now, most common for all 3 tested storage models are BIOS and OS performance settings and doing hardware NUMA alignment. Now, the first one is pretty straightforward, as it's just about putting the system used in the test into a full performance mode. On the well, this includes modifying BIOS settings in the power and performance tab, or whatever it may be called on your system, and use the most performance-focused option available. And on the operating system side, we tend to configure CPU frequency scaling governor into performance mode, which helps us avoid kernel lowering frequencies of the CPUs that we use in the test. Secondly, hardware NUMA alignment. This is about adjusting test systems' physical layout, test configurations, and used CPU masks in a way which in which all elements are preferably on the same NUMA node, or that cross NUMA is minimized. This allows to reduce the number of context switches needed to process the I/O between the elements, which generates less overhead and better performance results overall. For a simple example, when configuring a SPDK nvme over Fabrics target with, let's say, 1 NVMe SSD and 1 network interface, which are located on NUMA node 0, you should use a CPU mask for SPDK target, which will also uses CPU cores from NUMA node 0. Additionally, depending on the storage type tested, there might be some extra optimizations involved. And let's stick with using NVMe over Fabrics as an example. In this storage model, we further extend the NUMA alignment optimization by adjusting network interface IRQ settings. Default IRQ balancer used by Linux kernel is then disabled, and the cores which are used to handle interrupts are manually adjusted. And again, this allows us to minimize the cross-NUMA effect. Furthermore, for this type of storage model being tested, we adjust Linux kernel's TCP/IP sysctl settings in order to better handle high workload, high throughput of network traffic at 400 gigabits per second. And this is done mainly by increasing the size of the buffers used by the kernel TCP stack. All right, that's everything from me. Thank you for your attention, and I hope you enjoyed the presentation. Thank you.